Hello, everybody. Today's lesson is on section 7.4 from our calculus book on exponential change and separable differential equations. If you have the note template printed, you can follow along using that. You can also go to bit.ly/Dixon Math with a capital D and capital M to print this. It's in the Calculus 2 link under section 7.4. So we're going to start off with separable differential equations. So a differential equation is when you're given a derivative in terms of x and y, and so that's what we have here. So this is a differential equation. And then this is called an initial condition. So this gives us information about the graph. And so when you have a differential equation and an initial condition together, that's called an initial value problem. So both of these are initial value problems because they both have a differential equation and an initial condition. And so these are a group of differential equations called separable differential equations because we are able to separate the x's and the y's. There are many differential equations where that's not true. There's actually an entire course called differential equations that engineers usually will have to take as part of their curriculum. It's an entire course in solving differential equations. But the ones that we'll deal with in this course are a simpler variety called separable differential equations. And so what we're going to do is we're going to separate the x pieces and the y pieces. And so you can see in this first equation, we have an x here and an x here. We want to get those together. We have a y here and a y here. We want to get those together. And we want eventually the dx and the dy to end up on the top. So if we just multiply both sides by dx, so if I multiply both sides by dx, and then I divide both sides by y squared, what I end up with is 1 over y squared dy equals negative 4x dx. And now I can integrate each side. And so the antiderivative of the left side with respect to y, that would be negative 1 over y. And the antiderivative of the right side is, let's see, that's going to be negative 2x squared. And we need a constant of integration. We don't have to put one on both sides. You could if you wanted. If you imagine if you put constant 1 and constant 2, if we then move this constant over to here, then we would just have one constant at the end. So it's sufficient to just put the plus c on one side, not both sides. And now we can plug in our initial condition to solve for c. So this is our x value and this is our y value. And so we get negative 1 equals negative 2 times 0 squared plus c. So that tells us that c is equal to negative 1. And so our solution equation now is negative 1 over y equals negative 2x squared minus 1. And now we want to get y by itself. And so if we multiply both sides by y and divide by negative 2x squared minus 1, we would end up with y equals 1 over 2x squared plus 1. And so that is the solution of this initial value problem. So this is an equation now that satisfies these two conditions. If we take its derivative, it should equal negative 4xy squared. And if we plug in 0, we should get 1. The second example is very much the same. It's just written a little bit differently. It's written as y prime. You can always rewrite that as dy dx. In fact, that's what I suggest you do because then it makes it easier to separate the x and the y. With this notation, there's not an a change in x and a change in y component that we can separate. So it's better to write it as a fraction using the fraction notation, dy over dx, because remember that what that represents change in y over change in x. And those are two things that we can separate. And so now you have that differential equation with this initial condition. Go ahead and see if you can separate the x's and the y's, integrate, and come up with a solution function for your answer. So pause your video and press play when you're ready to check your work. Okay, so we have these y's that we want to get together, and so if we divide both sides by cosine squared y and multiply both sides by dx, we'll have 1 over cosine squared y dy equals dx. And then we can integrate both sides of that, and I'm going to rewrite the 1 over cosine squared as secant squared. And so the antiderivative of secant squared is tangent. So we have tangent y equals x plus c. Antiderivative of 1 is x. And so now we can plug in 0, 0 to get c. So tangent of 0 is 0, and 0 plus c, so c equals 0. And so that means our solution is here with c equals 0. So that would be tangent y equals x, or y equals inverse tangent of x. Okay, just take a moment to read this information, and then we'll work on example 2 next. So the key to this paragraph, the most important part of that, is that we make an assumption when we're working with exponential growth and decay and temperature change and things like that. We're making an assumption that the rate of change of the function is proportional to the current value of the function. For example, if you're thinking about money, exponential growth, the more money you have earning interest, the bigger your amount of interest is going to be. So your rate of change in terms of dollars per month would be bigger for a large bank account than it would be for a smaller bank account. So the amount of change that we see is proportional to the amount of money that was originally in the account. And so that assumption right there, when we write that in terms of calculus, as it says, the rate of change is proportional to the current value of the function. So the rate of change of the function is proportional to the value of the function. So k could be any constant. Okay, so as long as k is any constant, then we have our rate of change is proportional to the current value of the function. Or think of it this way, that the amount of interest that we make is proportional to the amount of money in the bank account. Okay, or in terms of population, the increase in the number of people per year is proportional to the number of people that live in the city. Okay, so we have a population example here. So the population of Smallville has a constant growth rate of 2.5% per year. The current population is 3,200. So this is an initial value problem. So what this is telling us is that our growth rate of the population, so the rate of change of the population with respect to time is 0.025 p. And this is giving us our initial value. So that's saying that the population now at time 0 is 3,200. So we have a differential equation. We have an initial condition. When those two things are together, that's called an initial value problem. So we have now set up an initial value problem, and so we can solve that same way we did the first two examples, by separation of variables. So if I divide both sides by p and multiply both sides by dt, I have 1 over p equals 0.025 dt, and then integrate both sides. I lost my dp here. Okay, so I again multiplied both sides by dt. I can write that here in red. So I multiplied both sides by dt, and then I divided both sides by p. All right, and so now solving that, we have natural log of the absolute value of p is equal to 0.25 t plus some constant. If we plug in 0 and 3,200, we have the natural log of 3,200 equals c. And so now we have natural log of p, and I'm getting rid of the absolute value because population is always going to be positive. And so then we get 0.025 t plus natural log of 3,200. And now we just need to solve for p. So if I raise e to the power of the left side of the equation and e to the power of the right side of the equation, then I end up with p equals e to the 0.025 t. I'm going to split this up into two different parts, times e to the natural log of 3,200. Because remember, when we multiply things with the same base, we add the exponents. So since we have added exponents here, I split that up into a product. And the reason why I did that is because this is just a number that we should be able to get pretty easily. Since e to the x and natural log x are inverses of each other, this number is just 3,200. So we have p of t is equal to e to the 0.025 t times 3,200, or written a little bit more clearly would be 3,200 e to the 0.025 t. And so that is our population model. So just by knowing the growth rate and the starting value, we're able to write a population model. So now we have a function that we could use to predict the population at any time. And that's exactly what the question was asking. Write a function to model the population x years from now, or it should be, actually I used t, but t years from now. You could change those to x's if you wanted to. Okay. So what we're going to do in example 3 is the same exact thing, except we just have some constant k. Instead of having the growth rate of 0.025, we're going to do it in the general case with k, and our starting value of our population is y sub 0. Okay, so those are just given constants. And so to come up with, if we solve this the same way we did previously, we would divide both sides by y and multiply both sides by dt. And so then I get 1 over y dy equals k dt. We'll go through the same steps. Integrate, we get natural log y equals there would normally be absolute value, but again, I'm assuming that my population or the amount of money in my bank account is positive, and then this would be KT plus C, and then we plug in the Y value for Y equals K times 0 plus C, so C equals the natural log of the initial value. Okay, so now from here I know what C is, so I have natural log Y equals KT plus natural log of Y naught, and raise e to the power of each side. And then we get Y equals e to the kt times e to the natural log of the initial value, and so then that just becomes y0, so we'll put that in front. So the population equals the initial population times e to the kt, and so that gives us a general form that we can use for anything that has exponential growth and decay. If k is a positive number, then we get exponential growth. If k is a negative number, then we get exponential decay. So to fill in the blank here, it's going to be y equals initial value e to the kt for k greater than 0 for growth and k less than 0 for decay. So remember, it's important to realize that y sub 0, or you can pronounce it y naught, is that's our starting value. So starting population or starting amount of money in our bank account, whatever it is that it's modeling. Okay, the concept of half-life means the amount of time. Half-life is a time period, and a half-life represents the time that it takes for half of an original amount to remain. So this radioactive element has a half-life of 7 years, which means after 7 years, half of its original amount remains, half of it has decayed. The original mass is 6 milligrams. Write a function to model this mass over time. Okay, so we know that if we start with 6 milligrams, that it's going to be equal to 3 milligrams. So if we're using this model, so y equals y naught e to the kt, and so if our starting value is 6, it will become 3 after 7 years. So that would be e to the k times 7, and then we can solve for k. And so if we divide both sides by 6, we get 0.5 equals e to the 7k. Take the natural log of both sides. Natural log of 0.5 equals e to the, or equals 7k. So then k equals natural log of 1/2 over 7, or negative natural log 2 over 7. Those are both the same number, so you can write that either way. And so now we can write our model as y equals 6e to the negative natural log 2 over 7 t. So let me try to write that more clearly. Negative natural log 2 over 7. So that's our model. Now we could plug in any time period and we would know how much of that radioactive element remains. So if we have a decay equation with a negative k value, we can do pretty much the same thing. So to find the half-life in general, we just put in half the original amount, so this would be 1/2 of y naught. So if we started with y naught, we have half of y naught e to the negative kt, and divide both sides by y naught. 1/2 equals e to the negative kt, and take the natural log. We get natural log of 1/2 equals negative kt. So from there, t, that's the half-life, is equal to natural log of 1/2 divided by negative k, or in other words, natural log 2 over k. And so that's using an equation where we already have the negative sign built in, so then k would be positive if we already know it's a decay equation. Newton's law of cooling is another example of exponential growth and decay. So as an object cools, its temperature is decreasing, and it's not the temperature itself that is changing exponentially. It's the difference between the temperature of the object, which is T, and the surrounding temperature. So you have, think of room temperature. If that stays constant, if you have a warm cup of coffee and you put it in a room, then eventually the coffee is going to cool and get closer and closer to the temperature of the room. Okay, so we have T is changing. That's that temperature of the object. T sub s is constant. That is our room temperature, and then T sub 0 is the starting temperature of the substance, so the coffee or whatever it is that's cooling. Okay. So for example 6, we have a bar of silver that is 100 degrees above room temperature now. 20 minutes ago, it was 125 degrees above room temperature. How far above room temperature will it be 15 minutes from now? Okay, so the actual temperature of the object is never given, and neither is the room temperature. But we can write these using this equation up here. We can say T minus Ts, so we don't know either one of those, is equal to let's see, right now it's Ts plus 100 minus Ts. So filling in here, the starting temperature started at 100 degrees above room temperature. And so the difference between those and so these TS's are going to cancel, so we're going to have right now, so 20 minutes later, the temperature is 125 above room temperature. So the temperature now we're going to fill in is T sub s plus 125. And then this all simplifies to just be 100 e to the negative k times 20 minutes. And then the TS's cancel. We get 125 equals 100 e to the negative 20k. So then that is 5/4 equals e to the negative 20k. Solve for k. Natural log of 5/4 equals negative 20k. So k equals natural log of 5/4 over 20. And now that we know k, we have our equation. In general, it's T minus Ts equals 100 e to the negative natural log of 5/4 over 20 t. So given that equation now, you could plug in any time, and you'd be able to find the temperature. So it says, the question now says, how far above the room temperature will it be 15 minutes from now? So I just plug in 15 minutes for lowercase t. T minus ts equals 100 e to the negative natural log of 5/4 over 20 times 15. And when you plug that in, that is 84.59 on the right side. So T minus TS equals 84.59. And then that tells us that T is equal to the surrounding temperature plus 84.59. So it's 84.59 degrees above room temperature. Okay, so you go ahead and try B. You can still use the same equation that we derived here and find the temperature 2 hours from now. So pause your video, work that out, and then press play when you're ready to continue. Okay, so we did this previous problem in minutes, and this one is in hours. So 2 hours is just going to be 120 minutes. And so now we can do T minus TS equals 100 e to the negative natural log of 5/4 over 20 times 120. And so then we get T minus TS equals 26.21. And so then the temperature is TS plus 26.21. So that means after 2 hours, it's only 26.21 degrees above room temperature. Okay, and that completes our notes today. If you want to do some extra practice problems, these are good problems on page 405 to give you lots of practice on these topics. Have a great day.